We continue from the previous problem where we launched a ball vertically upwards in an accelerating elevator. So the elevator begins from rest at level x and moves vertically upwards with an acceleration of a. When the elevator reaches level y, a ball is fired vertically upwards while the elevator continues accelerating upwards. In this problem, we have to find the maximum height of the ball, not from the ground, but from the floor of the elevator, or in other words, the maximum displacement between the ball and the floor of the elevator. And just to change the nature of the problem to a one we have previously solved, we treat this problem as a one where we have to find the maximum displacement between the two balls. So we fix the yellow ball to the floor of the elevator so it has the same velocity and acceleration as that of the elevator. And we have to find the maximum displacement between the red and yellow balls. And remember, it is not necessary that the maximum displacement would occur when the red ball has reached its maximum height from the ground. The maximum displacement could very well take place before the red ball reaches its maximum height with respect to the ground. As the elevator moves from Y to Z, the distance between the red and yellow balls keeps increasing. But as we shall see in the next step, if the elevator goes higher than Z, the distance between the red and yellow balls will begin to decrease. Also, it is important to note that this is not the scenario where the red ball reaches its highest position from the ground frame of reference. The red ball would continue to rise higher from this point on, but then the yellow ball will be rising at a faster rate, thus decreasing the distance between them. And you can see that as the elevator goes higher than level Z, the red ball also moves higher, but the distance between the red and yellow balls is now decreasing. Let's play this one more time in slow motion. So the distance between the two balls increases at first, that is between Y and Z, and you can see the red ball moving away from the yellow ball. In this stretch, the velocity of the red ball is higher than that of the yellow ball. Now beyond Z, the velocity of the yellow ball is higher, and the distance between the two balls now decreases. This is a case of the maximum height from the ground, but it is clearly not the maximum displacement as can be seen. What we are interested in is the maximum displacement between the red and yellow balls. So up to level Z, the red ball is faster, and beyond Z, the yellow ball is faster. And at Z, the velocity of the red and yellow balls is the same. Now this is very important. This means that at level Z, the relative velocities between the red and yellow balls will be zero. So the red and yellow balls, and therefore the elevator, will have the same velocity at a time when the elevator has reached level Z. And the maximum height or the maximum displacement condition occurs when the relative velocity between the red and yellow balls is 0. Since we want to find out the maximum displacement and we have no idea about how much time it would occur in, we can use the third equation of motion, which doesn't have time in it. And let's write the equation in terms of the relative displacements, velocities and accelerations of A with respect to B, or A with respect to the elevator. And we are now looking from the elevator's frame of reference. The important concept here is that when the displacement between A and E is the maximum, the velocities of A and E will be identical. Therefore, the relative velocity of A with respect to E would be 0, and that is the final relative velocity at a time when we are computing the maximum height. The initial relative velocity is VA with respect to E at point Y, when the red ball is shot off, with an initial velocity of VA with respect to E, which is at level Y. And the acceleration of A with respect to B, or A with respect to E, would be minus G minus A. The initial relative displacement would be 0 since they start off together, and the final relative displacement would be h since that is their separation which we have to compute. And we obtain the height or the maximum displacement between the ball and the floor of the elevator as V A with respect to E squared over 2 times G plus A. An interesting comparison between the ball which is thrown up vertically with a speed of v from the ground. It would also rise to a height of v squared over 2g. Let's also find how long it takes for a ball to get to the position of maximum displacement from the floor of the elevator. To obtain the time taken by the ball to attain the maximum height, we could make use of the first equation of motion, and we make the elevator E or the ball B as the observer. So we attach the frame of reference to the yellow ball, and we find the relative velocity and acceleration of the red ball with respect to the yellow ball. And we again make use of the concept that the relative velocity between the red and yellow balls will be 0 when the condition of maximum displacement is achieved. So the final relative velocity is 0. The initial relative velocity is VA with respect to E, which is the launch velocity of A relative to the elevator. The acceleration of A with respect to B or A with respect to E would be minus G minus A. So in this case, the final relative velocity is 0, and we get the time as VA with respect to E over G plus A. It is interesting that the ball will reach its maximum height in exactly half the total time of flight. And if you recollect, the total time of flight was 2 times VA with respect to E over G plus A. When a ball is thrown upwards from the floor of an accelerating elevator, the maximum displacement between the ball and the floor of the elevator occurs when the relative velocities between the ball and the floor of the elevator is 0.